Have you ever really thought about how we find the energy that powers our world? I mean, the stuff that's hidden miles beneath our feet, sometimes even under the deep ocean floor. Well, it's not about luck. It's a high stakes, high tech hunt that mixes geology, physics, and some absolutely massive engineering. So let's dive into this multi-billion-dollar geological odyssey.
So, really, how is it done? You can't just start digging. You have to think of it more like a massive detective story. Geoscientists are the detectives, the Earth's crust is the scene of the crime, and they are hunting for very specific clues that point to a very specific kind of buried treasure.
Okay, here's our roadmap for this whole investigation. We're going to follow the evidence right from the initial search to gathering clues, then building a solid case, putting it all to the test with a drill bit, and finally figuring out what we've actually found. Our investigation kicks off with the subsurface search, and right away, the sheer scale of the challenge becomes crystal clear. We're talking about searching for something you can't see, in a place you can't easily get to, and the financial stakes, well, they are enormous. The number one rule of this hunt is pretty simple. You do not drill blind. A single exploration well in deep water can easily cost over $100 million. And to avoid turning that into a $100 million hole with nothing in it, companies gather every single piece of data they can get their hands on. It's all about building a really detailed picture to shrink that huge uncertainty before you even think about spending that kind of cash.
So, how in the world do you gather clues from miles underground? Well, you use some incredibly advanced technology. This whole phase is about using sophisticated tools to, in effect, see deep into the Earth's crust. And here are the tools in our detective's kit. Now, seismic surveys are the big headliner for sure, but we've also got gravity and magnetic studies and even electromagnetic methods. And all of that tech is backed up by good old-fashioned geology. Studying surface rocks for clues and analyzing data from any wells that might have been drilled in the area before. Each tool gives you a different and totally vital piece of the puzzle.
The most powerful tool in the whole box is seismic. The way it works is just fascinating. Powerful sound waves are sent into the ground, they bounce off all the different rock layers, and then come back to the surface where these super sensitive sensors record them. By analyzing all those echoes, geophysicists can create a crazy detailed 3D map of what's going on down there. It is literally like giving the Earth a medical ultrasound to find hidden structures where oil and gas might be trapped. But seismic isn't the only trick up their sleeve. You've got gravimetry and magnetometry, which measure these tiny, tiny variations in the Earth's gravity and magnetic fields. This helps map out huge, deep structures, like massive underground salt domes that can warp the rock layers above them and create the perfect traps for oil. On the other hand, electromagnetic methods send electric currents into the ground. Now, since oil and gas don't conduct electricity very well, they're what we call resistive, they can sometimes be spotted directly, lighting up on the data like a big red flag.
Okay, so you've gathered all these different clues. What happens next? Well, the team has to build a compelling case. This is the part where terabytes of raw data get crunched and transformed into a single, viable target for drilling. It's the ultimate data-to-decision pipeline.
And this really breaks down that whole process. So on the left, you've got all your data inputs. On the right, that's where the analysis magic happens. Geoscientists use all this information to identify three crucial things. A reservoir rock, which is basically a porous rock, kind of like a sponge that can hold oil. A seal rock, which is a non-porous layer on top that traps the oil. And the actual shape of the trap itself. From there, they run risk assessments, estimate how much oil might be down there, and then, finally, they ask the most important question of all. Does this even make economic sense to drill? And all of that intense work leads to this one single crucial moment, the authorization for expenditure, or AFE. This is the final go or no-go decision. After months, sometimes years of work, a committee of experts reviews the entire case and they decide, do we approve the massive budget to drill? Do we send the team back to the drawing board to reevaluate? Or do we just scrap the whole thing?
If the prospect gets that green light, we enter the most exciting phase of all, the ultimate test. It is time to drill. This is that moment of truth, where all the theories, all the computer models, all the seismic images are finally put to the test against cold, hard reality. And these are the incredible machines that make it happen. I mean, whether it's a massive offshore drill ship like this one or a rig on land, these are the tools designed to punch a hole miles deep into the Earth's crust, just to see if that geological hypothesis was actually correct.
Now, the drilling itself is a highly choreographed multi-stage operation. It starts with preparing the site, then the rig drills the wider surface sections of the well before it begins that long, super precise journey down, sometimes for miles, to hit a target that could be just a few 100 feet thick. Once it reaches the target zone, a whole suite of sophisticated electronic tools are run to figure out exactly what they've drilled into before a final analysis is done.
So let's say the drill bit hits oil. Time to celebrate, right? The champagne corks are popping. Well, not quite yet. Finding some oil is one thing. Finding out if there's enough to actually make a profit, that's a whole other challenge. This is what's called the appraisal phase. During appraisal, the team really digs in to figure out exactly what they found. This means drilling more wells just to map out the size of the field, doing production tests to see how well the oil flows, and taking tons of fluid and rock samples. All of this new data is then fed into these complex reservoir models to get a really accurate estimate of the reserves.
Ultimately, this whole process from start to finish boils down to one key metric: the probability of commercial success, or POS. And this number isn't just about the chance of finding any oil. It's a complex calculation that asks, is there enough of it? Is the quality any good? Can we get it out of the ground efficiently? And, the big one, are we going to make money after spending billions on development? Only if that POS is high enough does the project actually move forward.
Which brings us back to our final question here. After seeing all the incredible science and the rigorous analysis that goes into this, what do you think? Even with all this amazing technology, the odds of a brand new exploration well being a commercial success can be as low as 1 in 10. So is this a calculated science? Or is it still the world's most expensive gamble?